Okay, lesson 3.6, calculus, we're talking about inverse functions. So, with inverse functions, it's kind of adding a layer to what we learned already. So we talked about relationships, which is just a mapping from one set to another set. This could be something like, x's to y. It could be something like shoe size to height. It could be any group from one set to another set. Right? I think when we talked about this in like Algebra 2, so last year, I think we talked about it as we started off talking about movie stars and the movies that they've been in, right? And that's a set to another set. So that's a relationship. Now, where did we go from relationships? After relationships, we talked about a different layer to the same topic, the relationship. How to restrict it a little bit more. Function. We've been talking about this whole time. So functions, which is no fickle picker. And what do we mean by no fickle picker?
There's only
Incorrect.
no, it's only
Every x only has one y value. So it means whenever you have an input, there's only one output that can happen, right? So it's really nice for predicting, right? Like I use the example of a remote control. If I hit the channel up button, it means that we can predict what's going to happen, which means the TV will go up one channel, right? So that's a function. If it was a relationship, if your remote control is a relationship, which sometimes it happens when they start to break, right? They wouldn't be very useful because sometimes you'd hit the up button and maybe the volume would go up, or you'd hit the up button and it might go 10 channels or turn off or whatever. It would get frustrating. So we look at the function. Now, what we're going to talk about now is a one-to-one relationship, which is not only is for every one x value there's one y value, but for every y value there's only one x value. Okay. Now I think when we talked about functions, we talked about not being a fickle picker, right? And I think in algebra 2 we used the example of like I, Mr. Davis, picked my wife, and I'm not being fickle about that, right? But the thing with the functions, can that picker or can that y value be popular? Can there be more than one input picking it? Yeah. So not really like marriage. This one-to-one is like marriage, right? I'm picking my wife. I'm picking my wife, and she's not being anybody else, right? She's off the market. Okay. Yeah.
So say like for the one-to-one, an x value has a y value.
You're talking about a function. So if you have an x value with a y, so like let's use a number. Let's say we have a point 1, 2. Okay, that means 2. My y value is off the table now. No other x value can pick 2. That means 1-to-1. Okay, so if I had 1, 2, and I had 3, 2, this is a function, but not 1-to-1. Okay. So that's the difference there. All right, so now when we talk about one-to-one, many functions, when they are reversed, are still functions. Okay, what do I mean by reversed? So what I mean by reversed generally is like saying if I have this is going to be a counter example, but like the TV remote, right? We said if you push the channel up button, there's an expectation of what's going to happen, right? Now, it means say the channel went up one channel, right? You could probably think about, and you could look at who has the remote. You could probably tell what they've done to the TV, right? This happens with my kids all the time. Ava, she loves grabbing the TV remote. For some reason, she always hits channel 1, which changes it to the Spanish channel. I don't know. Maybe she just really likes Spanish soap operas or something. So anyways, so whenever that happens, whenever I see the channel, right, so I'm seeing the output. I see the channel going to Telemundo or whatever. So Telemundo, then I can, okay, if I reverse this function, I know that somebody has pushed on the remote, which means that it's an inverse function, and I can figure out what's going to happen there. Mathematically, what that looks like, if I start with this equation here, y 3x plus 4, I can reverse it and make it 1/3 y minus 4/3 x. You'll learn how to process how to come up with that reverse function coming up. Okay? But just assume that this second piece is the reversed function of this first piece. And here's an example of what I was talking about earlier with marriages, right? So Mrs. Rob, you guys don't know who Mrs. Rob is? Mrs. Durbin. Mrs. Durbin's husband, his name is Rob, so she's Mrs. Rob. I don't know if that's her maiden name or what, but it's kind of a joke. Mrs. Rob. All right. So on this one, hopefully, marriage is going to be a one-to-one function, right? If everything goes as planned, one-to-one function. So not only did I pick Mrs. Davis, but Mrs. Davis is also picking me, which makes it a one-to-one function. I know. Yeah, this is how I explained it. I explained it how it's gone from a relationship to now, when I proposed, it was a function because I'm picking, and then when she said yes, and we got married, then it became a one-to-one relationship, and it was beautiful. It was so romantic there. All right. Okay. Shh. So let's look at these. We have three functions, f, g, and h. They have just 4 points each in them. I want to talk about which one of these represents functions, right? So does f represent a function? No, because if we look right here, we have the same x value, or they're giving me different y values out. Yeah, and then right here I have another two x's. So this is a relationship, right? Okay, what about g? Is g a function? No. So you have 0, 1, 2, 3. All of them are different. So is it a function? Function right here. 0, 1, 2, 3. Is this one a function? Function. Okay, so part B. Which of these functions are one-to-one? Now we need to look at the y values, right? And say, is there any y values that are used more than once? So we automatically don't need to look at the relationship one. So we go down to G and H. Here, what do I notice? Well, and I'll do it in green. What do I notice about these ones? 2 1s and 2 2s. Is this one a 1? No, so this is just a function, right? What about H? We have 1, 2, 3, 0. 1 to 1. This is a function and 1 to 1. All right, so for C, for each set that is a function, form a new set by reversing each ordered pair. Okay? Which of these new sets represents functions? So C, they're saying is if I take F, I'll do it in blue. So if I take F and I reverse, let's see, I reverse each one. So 0, 1, I plug 1, 0. I reverse the x, the input and output. Okay? And then the second point would be what? 2, 0. The third one would be 1, 1. And the fourth one would be 2, 1. Oops, 2, 1. So if I reverse it, which of these new sets are going to be functions? So it's reverse, and let's wrote f equals, right? And let me fix that a little bit here. So instead of f, because it's not f, so instead of f, maybe I'm going to write this. I'm going to write -1. We'll talk about that more later. But is the inverse of f, is it a function? No. Okay, now let's, in our minds, because I think around in our minds for G, if you flip or reverse the x and y's on G, is it a function? Nope. Because we end up getting those ones become our x's, right? And so we get more than one input value. What about h if I flip h? If I reverse it, does it become a function? Yeah, it looks like it will. Okay? Now, if we look at these results and about reversing it, which one of those, f, g, or h, which one was the only one that could reverse it was still a function? The bottom one, h. And what was h? It was a one-to-one function. What can we assume about one-to-one functions? You can reverse it and it's still a function. Okay. So, now, for example, we're going to do whether f is a one-to-one function for each of these. Okay? Now, when we do this, what we're looking for, is there any points? And so we're kind of looking for, I guess, a counterexample of two x's that pick the same y. So what we're looking for is, two x's that pick the same y. Okay. So that's a counterexample. All right, now, if we look at A, it should be pretty easy to count. Right? What's two x values in f of x here that's going to give me the same y output? Okay, so let's use 2. So we'll say f of 2 is equal to 2 squared. So 2 squared is 4, so f of 2 is equal to 4. Now what we want to do is we want to pick a second number that has that same answer, right? We want blank squared to be 4, but we want it to be an x value that's different than 2. Negative 2, right? So I go negative 2, negative 2 squared is the same thing as 4. F of negative 2 is still 4. Is it a one-to-one function? Is this one a one-to-one function? No, because of a one-to-one function means that if you put in two different x's, I should get two different y's. Okay? So this one's not one-to-one. Okay. Let's look at B. Okay, I'll put B over here. Is there any way that we can come up with two x's that come up with the same y on this one? What do you guys think? If you think there is one, it is. So 1? So okay, so f of 1 is 2 times 1 minus 1, which f of 1 is equal to, that's 2 minus 1, which is 1, right? Okay, so what's my second x value, which is going to still give me what 1 as an output? Negative 1. Okay, so let's try that. That worked for the last one, right? So we'll say negative 1. So 2 times negative 1 minus 1. Well, 2 is negative 2. 2 is negative 3. So that didn't work. Well, we tried one time, right? So if we just try one time, it doesn't really make it 1-to-1. But maybe make it 1-to-1, right? Maybe let's look at, maybe it would help, let's look at the graph of this. Okay, so let's graph this real quick. Put it way down here. There we go. So it was 2x minus 1, right? So say, oops, 2x minus 1. So what's my starting point? Negative 1. What's my slope? Up 2 over 1. And as I graph this, do you see any repeats on y's? No. Now, if we think about it, what test do we use on graphs to determine whether a function is a function or not? Vertical line test. So if we use a vertical line test to decide if it's a function, what are we going to use to decide if it's a, yeah, so this tells me function, right? A horizontal line test will tell me if it's a one-to-one, right? So now we're checking to see if there's any double y's. And is there any double y's? No. So is this one here, this 2x minus 1, is it a one-to-one? Yes. All right. I think. Here we go. Theorem 2, I don't care that you know it's theorem 2, but it says horizontal line test is, will test for one-to-one relationships, which we just talked about. All right, so draw a function that's increasing over the whole domain. Okay, what do I mean by increasing over the whole domain? The slope is what, and then when we talk about increasing, from which direction to which direction? Left to right, it's increasing, right? So the slope is positive, the slope is increasing. Does it have to be linear? Does it have to be a straight line? No. It just has to be increasing, right? So I won't make you guys all draw them right now, but right now just kind of visualize how you would draw an increasing function right now. Okay, for just a second, and then I'll draw mine. All right. So now I'm going to do my increasing function. Hold on, I already messed up. Is my increasing function linear? Was it the same as what you guys thought in your head? It probably shouldn't be, right? Since we have an infinite amount of possibilities, it'd be weird if we each thought the same way. But here I have this. Would this pass the horizontal line test? Did yours pass the horizontal line test? Is there any way to draw one that is increasing the whole time? Is there any way to draw one that would not be a one-to-one function?
X squared.
Well, x squared. Okay, so x squared looks like this. Is this increasing the whole time? It's decreasing for this first half, isn't it? It's decreasing to there, and then it's increasing, yeah. So this way? So what if it was this way? A sinusoidal. Is that increasing the whole time? No, because it only increases, like, see, it increases from here to here, and then from here to here. But it's decreasing right here, isn't it? So those are decreasing ones. So that one doesn't work. It's not increasing the whole time. Yeah. So it snakes upwards. Let's see. So like that? Straight upwards? Ooh, that is increasing. But wait, what did they say here? Is it a function? That one's not a function. The function has to pass the vertical line test, right? This one doesn't pass. But if we took this one, let's see if I can do this. So if we turn this one just far enough where it passes the vertical line test, like that. I gotta turn it a little bit more. There we go. I had to turn it a little bit more. Okay, so that passes the vertical line test. Is it one-to-one? But it's not increasing the whole time now, is it? It's decreasing from here. It's decreasing right there. Because it wasn't a function the first way. Yeah. Could it just go straight? Could it just go like this? So linear? So any linear, it seems like, would be, unless it was horizontal. All right. All right, so theorem 3 says if a function is increasing or decreasing the whole time. Okay? And we had a few examples of where it is and not increasing, decreasing. But if it's increasing or decreasing the whole time, then it has to be one. Any time that it switches from increasing to decreasing, then automatically it's not going to pass the horizontal line test, which means it's not going to be one-to-one. All right, so inverse of a function. This is what we can learn. It's the reverse of a one-to-one function, and so noted as f to the negative first power, right? And we call that inverse of f. Right. If it's not one-to-one, then it doesn't have an inverse, and this does not exist. All right. Inverse functions are always one-to-one, and then if we think about reversing everything, okay, we're going to be reversing functions. So if I reverse a function, it makes sense that the domain of f is the range of inverse of f, right? So we just switch the domains and ranges. And the range of f becomes the domain of inverse of f. All right. So let's talk about how we're going to do this. Theorem 5 says that if you do composition function of your function in your inverse, you're going to get out what you started with. Okay? I mean, it's almost like saying, like we use my TV example. Okay? I use, it's channel 1. I look at the TV, it changes to Telemundo. Right? And then from there, if I look back, I see the TV change to Telemundo. Now I look back to the remote, and what do I see? I see Ava hitting the 1 button, right? So it leaves you where you started at. So we're going to use Theorem 5 to see if so we're going to see if these are inverse functions of each other. So what Theorem 5 says that if I use a composition function between these two, I should end up with x, right? So I'm going to say f of g of x. All right. So what I'm going to do is I'm going to go, what this says is I'm going to take f of my x and plug in g of x. So I'm going to say f, take out x, plug in g of x. Okay. So I'm just doing composition what we did last chapter or last lesson. So this is instead of f of x, I'm taking out x and I'm plugging in g of x. So down here in red, I have f of x. I took out the x and I plugged in g of x. I plugged in g of x there. Okay, so I just did the composition part.
Where are the three in red come from?
3 in red came from this 3 right here.
All three? Okay.
So I have 3 instead of x. I'm not using x, I'm using g of x. So I have 3 g of x, 3 g of x, and minus 7 on the outside. Minus 7 on the outside. All right. All right. So what we should end up with if these are inverse functions is just x. If I simplify this, I should get x out. Well, what happens here? What do I need to do first when I do my, I guess this is a problem. What happens to 3's? 3's cancel out, leaving me with x minus x plus 7 minus 7. What do those do? Cancel out, leaving me with just x. Are those inverse? So are these two inverses of each other?
Yeah.
All right, good. Let me look. This is a good spot to stop for today, and we'll pause and we'll finish this up tomorrow.